Fire is the rapid oxidation of a material in the chemical process of combustion, releasing heat, light, and various reaction products. Due to the uncontrollable nature of fire, vegetation is a leading catalyst for fire's progression and growth. Forest fires are unpredictable because they vary in size, speed, and have the potential to change direction unexpectedly. Biomass burning causes a wide range of environmental impacts to the earth. Due to advancements in technology over recent years, satellite remote sensing has become well suited to assessing the area of biomass burning and is a prerequisite for estimating the released emissions at regional and global scales. These emissions influence the Earth's atmospheric chemistry, radiation budget, and overall climate. There are also several ecological effects that alter the biological nutrient cycle and modify vegetation patterns that add to the loss of animal habitat and biodiversity. The two most commonly used satellite-based techniques for measuring burned areas are thermal hotspot detection and multi-temporal NDVI analysis. The goal of this video is to introduce you to a new type of technique called HANDS and compare it to results to hotspot and NDVI analysis in various studies to determine if it is a credible method. With using hotspot detection, fire thermal energy is used to identify active fires using the mid-infrared channel. The primary limitations in hotspot analysis is that it only represents a series of burn activity snapshots, which can allow for active fires to be missed due to cloud cover. It may also overestimate large proportions of small, sub-pixel fires that may cause saturation in channel 3. This technique for assessing burn areas detects vegetation damage before and after a fire. Its advantages compared to hotspot detection is that the indicator of the fire remains detectable for a longer period and making it capable to map burned areas that the hotspot detection is missed. Its limitation is that in NDVI differencing assessment, it calculates areas affected by drought, seasonal vegetation, harvesting, and cloud contamination in the post-fire composite.
The objective of this study was to test HANDS, a new method for burn area mapping. It combines the strength of hotspot detection and NDVI differencing strategies. To evaluate the performance of HANDS, the researchers applied the technique to mapping burn areas across Canada in 1995 and 1996. The results were then matched against Canadian Forest Service fire statistics and province-wide GIS burn surveys. 3 types of input data were required for HANDS: a binary mass of the detected hotspots, post and pre-fire NDVI composites, and a vegetation mass developed from a land cover classification of Canada. These datasets were all derived from 1.1 kilometer resolution AVHRR imagery.
There were 10 steps in order to combine the hotspots data and the NDVI data. First was to normalize the NDVI composite data for post-fires and pre-fires. This was done by taking just the average NDVI values, not the hotspot values, for both composites, and then shifting the post-fire values to equalize them. The next step was to calculate the NDVI difference by subtracting the pre-fire composite from the normalized post-fire composite. The negative values in the resulting NDVI image equal to the burnt pixels. The third step was to confirm hotspots using NDVI difference. Here, any areas that were selected as hotspot pixels within the NDVI difference areas are labeled as confirmed burnt pixels. The next step was to calculate the regional NDVI difference statistics using mean and standard deviation of all the confirmed burnt pixels. Then a regional NDVI difference threshold was applied. For each block, pixels that had NDVI difference greater than +1 from the mean of the confirmed burnt pixels were selected. A threshold was placed to isolate pixels of potential burnt pixels that were not identified as hotspots. After the threshold, a filter was applied to smooth the burnt patches and reduce any noise in the image. The figure shows the results after the filter was applied. Then the burnt pixels were connected, clusters were created, and a unique code was assigned to each one of them. In the next two steps, the NDVI difference statistics was calculated again, using the mean and standard deviation of local, not regional, NDVI differencing for confirmed burnt pixels, and another threshold was applied. The final step was to eliminate all false burnt clusters. So the pixels were grouped into clusters. These clusters can account for time of fire and period of regression. In the end, the threshold was derived by examining the amount of hotspots detected within the polygons from the 1995 provincial burn surveys. As you saw in the images, any clusters containing less than 10% of the confirmed burn pixels represented noise and were not counted as major forest fires.
The aim in using Hand's algorithm was to harmonize results for burn area mapping from hotspot detection and NDVI differentiation to see how closely the results matched to the official burn area survey data. After running the algorithm, the burn area estimates of the 1995 fire season increased. Hands was able to detect 96% of the Canada-wide burn area in 1995, estimated by the National Forest Database Program. Provincial estimates were also consistently close to national database values as well. The study found that Hands was not able to detect burns that were less than 10 square kilometers in area. Burns of this size were insignificant as they accounted for only 3% of the total forest burn area in Canada from 1990 to 1995. A potential problem with Hands is that it shows errors of commission. For example, the algorithm detected burns larger than 50 square kilometers that were not identified by the surveys. In some individual burns, boundaries derived using Hands differed significantly from those indicated in the provincial surveys, and also identified unburned areas within a large burn polygon. These areas may have been burned areas with minimal canopy damage. These commission errors may have propagated over from the hotspot and NDVI data. To assess the ability of Hands to properly detect burn areas, the IGBP algorithm, a contextual fire detection algorithm, was used. The algorithm had similar detection success rates as Hands. It was able to detect 48% of the burn area compared to 60% detected by the Canada Fire Detection algorithm. Results obtained from the Hands algorithm are better match official burn survey data compared to other algorithms.
Overall, the algorithm was very close in approximating actual burn boundaries, better than most other algorithms. In some cases, the technique was able to identify burns not even shown in ground truth surveys. On the other hand, Hands did detect a few burns that weren't actually there. However, these errors were attributed to faults in the quality of the NDVI composites as opposed to the algorithm itself. Hands can be adapted to other biomes and environments provided that hotspots are sufficiently detectable, burned and unburned vegetation can be spectrally told apart, appropriate satellite imagery is available, and multi-temporal differencing can be performed over a reasonable time interval. The recently launched spot vegetation instrument and planned space-borne sensor MODIS should allow these requirements to be met.
In 2006, the Hands algorithm was used to map out burned forest fires in California. They adopted the ideas of working with Hands algorithm following the basic procedures of normalizing the NDVI post and pre-fires, calculating the mean and standard deviation of NDVI decrease, and adding in confirmed hotspot data. Overall, the results were compared to the California Department of Forestry and Fire Protection and were found to be conclusive and accurate. From these and other studies, Hands algorithm has successfully been altered to fit different environments other than boreal forests and have been proven to be quite effective in detecting and mapping burnt scarred areas over these large, vegetated regions.